All right, good morning. I know more folks will be logging in, but I'm going to just get started with some introduction slides, and then hopefully everybody will be online by the time Russ starts. So welcome to our webinar this morning. Thanks for taking the time to join us for today's workshop on heat pumps for residential heating and cooling. Oops, went a little too quick. So my name's Christine Condon. I'm an energy and sustainability analyst with the County of Sonoma in the Climate Action and Resiliency Division. I'll be your host today. I'll be monitoring the chat for questions, which we'll answer at the end of the presentation. I've been with the division, the Energy and Sustainability Division, since 2017, and our division recently merged with the Climate Action and Resiliency Division. I'm a certified energy analyst and a lead AP, and I work as a technical advisor for county projects and for the division's many programs. Our guest presenter today is Russ King. Russ is a licensed mechanical engineer with over 30 years of experience practicing and teaching in the area of residential HVAC design, which is heating, ventilation, and air conditioning, as well as energy code compliance. And I'll let him tell you a little more about himself at the start of his presentation. For this morning's workshop, everyone is muted, so please enter questions into the chat. And again, we'll address those at the end of Russ's presentation. The slides and the recording of the workshop will be sent out in a few days. If you haven't received them, and they'll be sent to everyone who's registered. So if you haven't received them via email in about a week, be sure to check your spam folder. And if it's not there, then reach out to our office at 707-565-6470 or energy@sonoma-county.org. And not many people realize that the county has a climate action and resiliency division, formerly the energy and sustainability division, along with there's a water agency and land management section of the division. And if they do know that there's a division like this, they don't realize the number of services that we offer to the community. The Energy and Sustainability Division was created in 2006 to address internal county energy use in order to mitigate climate change through greenhouse gas reduction. And in 2009, our Property Assessed Clean Energy Financing Program, the Sonoma County Energy Independence Program, also known as SCIPE, was introduced. SCIPE was the first and is the longest running residential PACE program. Again, stands for Property Assessed Clean Energy Financing. The program allowed property owners to finance energy and water saving improvements as a tool to reduce greenhouse gas emissions. And the program has since been expanded to include wildfire safety and seismic strengthening improvements. And since that time, we've added a number of resources and services. Our primary focus is on buildings and behaviors, and we assist customers through a variety of services. We offer sustainability workshops, green business certifications. We educate folks about financing and rebates. We maintain a qualified contractor list for the Sonoma County Energy Independence Program, which is a great tool for finding local contractors who service Sonoma County. We work on public and K-12 building audits. We offer specialized contractor trainings and no-cost consultations and project planning. Here's a little slide of our fall workshop series. You can go to our website and register for any of these. If you're interested in any past webinars, you can actually request the recordings and the slides, and we'll forward those to you. You just have to register and contact our office. So I wanted to talk about a couple of programs that are going to be related to Russ's conversation today. These programs are available to offer some pretty substantial rebates for heat pumps and other high efficiency technologies and building envelope improvements. The Bay Area Regional Energy Network provides rebates to the 9 Bay Area counties in this map here. And these rebates and incentives are funded by the public purpose program surcharge on your utility bill. So there are many types of rebates available through the BayREN program. It's the Home Plus program. There's air sealing, insulation, duct sealing, all things that can really help reduce the size of the equipment that you need. Rebates for the equipment itself, water heaters, and specific incentives for electrification. The program requires that you use a participating contractor and this is very beneficial for the consumer, where you have specially trained building performance contractors who are vetted through the program requirements. They manage the paperwork. There are quality control checks on their work, and safety testing is required for their to make sure everything's safe in your home when the work is complete. There's a contractor search tool on the BayREN website that makes it really easy to find contractors that serve your area. Here's a list of some of the measures that are available, the incentives for duct sealing, for example, attic insulation, highest priority. If you don't have good attic insulation, definitely take a look at this, really important, and others. Here's some high efficiency heating and cooling measures. Water heating incentives are really robust right now. So if you're interested in a heat pump water heater, BayREN's got one for $1,000. Their heat pump incentive also $1,000. And then some electrification incentives for appliances. And then some other bonus rebates. So go to their website, take a look. If you have questions, they have energy advisors that you can talk to. Their website's real comprehensive. So another real wonderful opportunity that we have in Sonoma County is the Sonoma Clean Power Advanced Energy Center. This is an educational facility where you can actually see equipment that you're interested in, like heat pumps, actually installed. And there's nothing like that, actually, to get an understanding of what things really look like, the size, how they'd fit into your home. And the Advanced Energy Center offers incentives, and we have these heat pump incentives listed because they're very robust. They just updated those, and they can be stacked with the BayREN incentive. So if you have a high efficiency air source heat pump, for example, that you want to replace, you can, and you qualify under the different program requirements, you can potentially be eligible for up to $4,000 for a heat pump system. We also offer the Property Assessed Clean Energy Financing Program in our office, where you can finance over 100 improvements with financing that becomes paid back through your county property taxes. You can borrow with terms of 10 or 20 years. The interest rate is fixed, and the fees are low pass-through fees. It's a municipal program, so it's all about consumer protection and very low fees. This is a financing program that's attached to your property and not your personal credit. So that can be very beneficial. Lots of different improvements. You can contact our office for more information. And here's just a list of kind of eligibility requirements for the program. Again, you're going to get these slides, but I'd like to roll into, oops, let's not get to questions yet, roll into Russ's presentation, because he has a lot of great information to share. All right, Russ, I'm going to stop sharing.
How's that? Can you see those both sides?
Yes, looks
awesome.
Good.
Great. Awesome. Well, welcome everyone. It's so nice to be here to be able to come talk to you about heat pumps. That's kind of the hot term these days. I'm sure you've seen a lot of discussions about it. And so today's class, we're going to talk about heat pumps specifically for residential space heating and cooling. Okay. So today's class is sponsored by Sonoma County. Thank you guys very much for hosting these trainings. You guys do a great job putting this stuff on for everybody. So today's agenda, we're going to talk about, we'll do a brief introduction. We're going to talk about some terminology. I think before you start talking about heat pumps and switching, your gas furnace to your heat pump and stuff like that to a heat pump, you really need to understand why you're heating and cooling your house and how you're heating and cooling your house and what are the important factors to keep involved. So we're going to talk about some terminology. We're going to talk about some really super basic thermodynamics and the refrigeration cycle. I'm always very cautious. It's one of the greatest cures for insomnia is to start talking about thermodynamics. So I don't want to put anybody to sleep. But there's some really interesting stuff that happens. I think the whole refrigeration cycle, once you understand it, it's really fascinating how it works. And so hopefully I can kind of get that across to some of you guys. And then we're going to talk about the advantages of heat pumps for space heating over gas, okay, over gas furnaces. And then we'll talk about some of the different types of heat pumps. There are different types available out there, different configurations, different sort of orientations of how they control via the indoor unit, the air handler, and the condenser, the outside unit, things like that. The technology has really come a long ways. So we'll talk a little bit about that, and then at the very end, hopefully, we have some time for Q&A. And I'm happy to stick around as long as we need, but we are on a kind of a strict schedule here. All right, so introduction. Again, my name is Russ King. I'm a licensed mechanical engineer in 3 states, and my company is called Coded Energy, Inc. We've developed a 3D HVAC design software, and we do a lot of training and consulting and things like that. I started working with the California Energy Code in 1988, so that's going on 34 years now. And then I learned how to do residential HVAC design, and I became a licensed mechanical engineer in, I want to say, 96 or something like that. So I've been doing this for a while. And I've seen a lot of changes, and I'm really excited about the changes that are coming up, actually. It's about time some of these things are happening. My email, if you care to get a hold of me, is russ@coded-energy.com. I have a blog where I talk about HVAC stuff. I get a lot of homeowners going to the blog and asking questions there. So it's not intended for professionals in the HVAC world. It's kind of a general topic, and it's russellking.me. And our website is quickmodel.com. We have a YouTube channel about HVAC design. It's called Quick Model. Just go to YouTube and search for KWIK model. And then I also wrote a book, HVAC 1.0, Introduction to Residential HVAC Systems. It's a really basic HVAC book. I wrote it. I don't own the rights to it anymore, so I don't make any money from selling copies or anything like that, but it's still a good book. I recommend it to people. It's used in a couple community college courses as a textbook. So there you go. All right. So to really appreciate heat pumps, you must first understand a little bit about how and why we cool our homes. Okay, so I'm going to get really basic here. Obviously, the main reason is for comfort, and in extreme climates for safety, for health and safety, right? Las Vegas, air conditioning is a health and safety issue. You have a lot of retirement communities there, and when it hits 115 degrees, you want the house to stay comfortable, or people literally start dying. It's a very important thing. So health and safety is also an issue. Now here in the Bay Area, we have a very mild climate, so it's not as big of a deal, but we do have heat waves, we do have cold snaps and things like that. But the main reason is for comfort, right? It's to be comfortable, okay? And if you're, elderly people, keeping it within a certain range could also be considered a health and safety issue, and it doesn't have to be extreme temperatures. So the problem is that heating and cooling house, it can use a lot of energy, and you have a lot of houses using a lot of energy, and excessive energy use has its own negative impacts. So we want to be as efficient as possible, okay? And by the way, HVAC, I think Chris mentioned this, but HVAC stands for heating, ventilation, and air conditioning. We're not going to talk too much about ventilation. That's an entire topic unto itself, is how much fresh air does a house need and things like that, indoor air quality. We're primarily going to be talking about thermal comfort today, okay? So HVAC, heating, ventilation, and air conditioning. The main goal of an HVAC system is to maintain a constant temperature in a house, okay? That's very important, constant temperature. When you design a heating and cooling system for a house, you are assuming that that system is there to maintain a constant temperature. So if you don't operate your heating and cooling system to maintain a constant temperature, if you mess around with the thermostat, you turn it off during the day, you come home, you turn it on, you turn it off, turn it on, you're not using the system the way it's designed to be used, okay? So and the other thing you have to realize is don't think of coldness, okay? Think of heat. Heat, when you cool a house, you're removing heat. When you heat a house, you're adding heat. So it's all about heat, heat either coming or going, okay, into or out of a house. So houses lose heat in the winter and they gain heat in the summer. To maintain a constant temperature in the winter, the heater must provide BTUs at least the same rate that they're being lost. So if they're escaping at a certain rate, we need a heater that'll put them back in at least that same rate, so the same number of BTUs stays inside the house to maintain a constant temperature. And then the same is true in the winter. And a lot of people think, oh, air conditioners put coldness into my house. It's air conditioners blowing cold air, so it's putting coldness into my house. Well, that's not exactly what it's doing. What it's doing is removing BTUs that are coming in from the outside. Okay, BTUs come in through your windows. When the sun shines through your windows, those are BTUs coming in. When hot air leaks into your house, when heat conducts through the walls, those are BTUs coming into the house, and you have to remove those BTUs, okay? And when you remove the BTUs from the air, you make the air cold, and then that cold air gets recycled back into your house. So you're not adding coldness, you're removing BTUs. So always think of it in terms of BTUs. That's very important, okay? All right, so some terminology. BTUs. So a BTU is a British thermal unit, okay? Not sure why we don't use American thermal units, but we use British thermal units. That's what we've been using forever. This is a unit of energy that is approximately equal to the amount of heat stored in a wood match. So if you take a wood match, you light it, you let it burn all the way down, drop it, you've just released 1 BTU of heat into the air, okay? So when you think of, if you go look on your furnace and they say it's a 40,000 BTU furnace, what they really mean is BTUH, BTUs per hour, okay? So a 40,000 BTU furnace means that it's putting 40,000 kitchen matches worth of heat into your house in 1 hour, okay? And air conditioners are rated in the same way, but instead of adding heat, they're removing heat. So think of it, if BTUs are hard to conceptualize, think of it as kitchen matches. I got a 40,000 kitchen match heater, and my air conditioner is removing 20,000 kitchen matches per hour of heat from the house, okay? So that might help too. So on some of these diagrams, we're gonna represent BTUs with these little flying kitchen matches, okay? All right, so here we go. Another thing is tons. Why do we call air conditioners tons? And why do we rate them in terms of tons? Well, this goes way back, all right? Way back to before we had mechanical refrigeration. We would buy ice by the ton. So if you owned a warehouse where you kept something cold, you had to buy ice by the ton. So you'd buy 5 tons of ice. Well, it just so happens that 1 ton of ice has about the same cooling capacity as 12,000 BTUs per hour. In other words, it takes 12,000 BTUs per hour to melt a ton of ice. So a ton of ice will absorb 12,000 BTUs from wherever it is, whatever big insulated box it's in, okay? So 12,000 BTUs per hour is sort of the nominal cooling capacity of a ton. So when a manufacturer manufactures an air conditioner, they shoot for those increments of 12,000 BTUs. So they've got, but they do it in half tons too. So you've got typically 1.5, 2, 2.5, 3, 3.5, 4, and then 5-ton units are going to be around, say, a 2-ton unit, 2 times 12,000 is going to be around 24,000 BTUs cooling capacity. So that's basically what a ton is 12,000. You can actually go look at your condenser, and after you get used to reading model numbers, you can determine the tonnage from the model number. There'll be numbers like 024 and 048. You divide that by 12 and get the tonnage, okay? But we call that the nominal capacity. That's what we call that unit. We're gonna call that unit a 4-ton. We're gonna call that unit a 5-ton. Has nothing to do with the weight, okay? They're much lighter than that. They represent a ton of ice. The reason we call it the nominal capacity, we're just going to call that unit a 4-ton, we're going to call it a 5-ton, is because the actual cooling capacity whether it's 12,000 BTUs per ton, it might be less than that, or it might be more than that, depending on a whole bunch of factors. The actual design capacity is different depending on a bunch of different things, but we just call it a 4 ton, we call it a 5 ton, okay? But then in order to determine the actual capacity, you got to know what's the outdoor temperature that it's operating at, how much airflow is blowing across the coil, what's the humidity, you know, things like that will usually reduce that 12,000 by a certain percent, okay? But when they test the unit, they test it at certain design test conditions. They get close to the nearest 12,000 BTUs, and then that's what they call it, the 4 ton and the 5 ton. Okay, but I just want to let you make sure you understand it's a little bit more complicated than that, but that's fine for, you know, just normal discussion. All right. Another important term is load. What is the load on the house? So we have a cooling load and we have a heating load. The cooling load is in the summer, it's the number of BTUs that are coming into the house. Where are those BTUs coming from? Well, they're coming from the outside. So you've got a certain number of BTUs in the house and it's hotter outside. So there's more BTUs outside than there are inside. The BTUs outside are more dense, let's say, and they're coming into the house. And you can calculate that. You can estimate that. If you know the indoor temperature, you know the outdoor temperature, and you know the properties of the various surfaces, you know the areas of the walls, how much insulation's in them, what kind of windows you have, how leaky is the house. You can calculate how many BTUs are coming into the house on a hot day, okay? So the cooling load is the number of BTUs per hour that the air conditioner has to remove in order to maintain a constant temperature. So if you've got a certain number of BTUs coming into the house, remember I said that the air conditioner has to remove those at least the same rate, okay, if you want to maintain a comfortable temperature. If they're coming in faster than the air conditioner can pull them out, they get more and more dense, and then the temperature goes up, okay? So the load is a calculated number to help you size the air conditioner. All right. And then cooling is the process of removing heat from the house. So when you cool something, you remove the heat. So consider an air conditioner that has a tested to have a cooling capacity of 24,000 BTUH, BTUs per hour. That means it can remove 24,000 kitchen matches worth of heat from the house in 1 hour. Now, will that cool the house? Well, it depends on the load, right? You have to do a load calculation to determine if that's going to work. And if you do a load calculation on your house, and your load calculation comes out at 23,000, 24,000 is good. That's a little bit more. That's what you want. If your load calculation comes out at 28,000, then your 24,000 is not going to keep up, and the heat's going to come in faster than it's leaving. Okay. Heating load, same thing, it's just the opposite. There's more BTUs inside the house. They're more dense inside the house than they are outside the house. So they're going to escape. The BTUs are going to leave the house. And a load calculation is a calculation of how fast that happens. How many BTUs per hour leave the house at a certain condition on a cold day. Okay, we're going to define that cold day. We're going to define that hot day. Those are the days that we're kind of call those design days. Those are the days that we want the air conditioner or heater to work on. Okay, but the point is that a load is a calculated number, okay, that you use to size your equipment. If you don't do a cooling load, if you don't do a heating load, you're just guessing. All right, and that happens unfortunately way too much. A lot of people just say, oh, you know, how big is the house? Oh, there's this old rule of thumb out there, 500 square feet per ton. So you got a 2,000 square foot house divided by 500, that's 4 tons. Ah, it's perfect size for a 4 ton. That's not how it works, okay? Load of a house is way more dependent on glass area and glass direction than it is on the square footage of the house. You can have a very small house with a lot of glass will actually have a higher cooling load than a big house with a little bit of glass. So basing load calculator, basing sizing of equipment on the square footage of your house is a bad idea, okay? But it's way too common. Okay. Heating is the process of adding BTUs. So the load calc is calculating how many you're leaving, and then you size your furnace or you size your heat pump, or you size your heater to add those BTUs back in at least the same rate. Okay, so a 30,000 BTU hour furnace is adding 30,000 kitchen matches worth of heat in an hour. And again, whether that's big enough or not depends on your load calculation. All right. So to maintain a constant temperature in the house, the rate of heat coming in must equal the rate of heat going out. The capacity of the equipment is how much heating or cooling it provides. Okay, so think of that as the supply. You got supply and demand. Supply is what you're getting from your equipment, whether it's the heater giving you BTUs, and demand is what the house needs. Supply could also be how many BTUs of cooling does it provide, and demand is what the house needs. So it's supply and demand. It's balancing those two things. So good equipment size is the ability to match the equipment supply, what it gives you, capacity, to the house's demand, its load, whether it's heating or cooling. Okay, that's very important. And like I said, if you're not measuring the load calc, if you're not calculating the load calc, that's why we call it the calc, load calculation calc. Otherwise, it's a load guess. If you're not calculating that number, you're just guessing. And what typically happens if they just guess, what are they going to do? If you're just going to guess and you're going to put a piece of equipment in it, are you going to guess high? Or are you going to guess low? Well, you're going to guess high. You're going to say, I'm going to put a big old air conditioner on there just in case. I'm going to put a big old furnace on there just in case, because I'm cutting corners on doing load calc. So I'm going to play it safe and put in a bigger piece of equipment than what the house might actually need, because I'm lazy, because I don't have time, because it's too expensive, it's too complicated to do a load calc or whatever. So that's very, very common, is they oversize equipment. And you might say, well, where's the harm in that? It's like putting a bigger engine in your car than you really need, right? Well, the harm is that it can make your car run very poorly by putting too big of an engine in it, and it can make it run very expensive, right? Not very good gas mileage and stuff like that. Same thing for a house. So sizing the equipment to the load is very, very important for efficiency, and hopefully I can demonstrate to you for comfort as well. So undersizing is when the load of the house is greater than the capacity of the equipment. Your equipment's too small for the load. It can't keep up, okay? Let's say, for example, using an 8-gallon per minute pump when your tank is losing 10 gallons per minute. You got a tank of water and it's leaking 10 gallons per minute, and you're refilling it at 8 gallons per minute, the water level is going to drop down, okay? There's a great analogy of a house being like a tank of water, okay? So undersizing is when your equipment is too small. Oversizing is when your equipment is too big. It's when your equipment, the capacity of your equipment is much greater than the load of the house, okay? That's like using a 14-gallon per minute pump when it's only losing 10 gallons per minute. So you're putting it in really fast, and then your water level starts building up, okay? So oversizing and undersizing, that's pretty straightforward. Now, when we do a load calc, we do it at certain design conditions, okay? So when I say your air conditioner has to work on a hot day and your heater has to work on a cold day, well, what's a hot day and what's a cold day? Those are statistically derived numbers that are specified by code. Code requires that you pick a certain temperature based on the city that you're in, okay? So here's an example of the table that we use, okay? Design conditions are specified by code for indoor and outdoor temperatures at which the loads are calculated. These are not the very worst loads, the very worst temperatures expected each summer and winter. You might say, gosh, we just hit 100. Oh, I live in the Sacramento area. We hit 114 or 115 a couple weeks ago. That was insane. So you might say, gosh, I want to design my air conditioner to work on a 115-degree day. That's not a good idea. Okay, I'll explain why. Same thing for the winter time. You might say, so let's look on here. So here on this table, we got Sebastopol. Sebastopol is in your guys' area, and it says, by the way, we use a number called the 1 percentile day. And what that means is 99% of the time, it's cooler than this number. But that also means that 1% of the time, or just less than 1% of the time, it's hotter than this. So when we pick a design temperature, we are by definition picking a temperature where it's going to be exceeded 1% of the time. But 1% is not that much. 1% is very, very tiny amount of time. And that's not days, that's hours, okay? It's not 1% of the days it's going to exceed that, it's 1% of the hours. So if you look at a temperature graph, it gets very hot during the day, it peaks, and it comes back down. 1% of the time, that peak is going to be above that number, and it's going to be for a very short period of time. And you can deal with that. There's things you can do to make your house deal with that, okay? All right, so we use a number called the 1 percentile day, and in Sebastopol, it's 95 degrees, okay? Does that seem hot or cool to you? Have anyone live in Sebastopol? Does it get above 95 degrees very often in Sebastopol? And you might say, gosh, yeah, a few days ago, it hit quite a bit warmer than that. But that's the peak temperature of the day. Now, it wasn't at, let's say the other day hit 98. It wasn't 98 all day. It was only 98 for a very short period of time. So don't fall into the trap. HVAC contractors do this all the time. And they'll say, oh, your design temperature is 95, but gosh, that seems kind of low to me. I think we should design your system for 100 degrees. Don't fall into that trap. It's not allowed by code, for one thing. And it's just a way for them to justify putting in bigger equipment. Okay, so be careful of that. Then on the cooling side, we use a number called the winter median of extremes. And in Sebastopol, that's a chilly 24 degrees is what we designed to in Sebastopol. Okay, so those are required by code. And don't stress over those numbers. They're, you know, they're very well-proven numbers. And because air conditioners and heat pumps and furnaces only come in certain increments, you're almost by definition going to be slightly oversized, okay? Because you're not going to pick up, they don't make equipment that's exactly the same capacity as your load. There's only certain increments. So you're going to pick the next larger one or the next smaller one. If it's really, really close, it's okay to pick the next smaller one. But even so, there's some slop and there's some safety margin built into the load calcs, okay? All right, so here's the other thing. If you're designing for a temperature that it's going to be cooler than that 99% of the time, your system needs to work on those milder days, right? And the problem with air conditioners is they're either on or they're off. They're either blasting cold air into your house or they're off, okay? Now they make fancier ones that have stages and stuff like that, but basically they're an on or off system. And oversized equipment, oversized air conditioners will cause more comfort problems than undersized air conditioners, because in oversized equipment, it's extracting BTUs much faster than they're coming into the house, and so it has to shut off. So when it gets to a certain point, it shuts off. That's what your thermostat does. Your thermostat says, oh, that's enough, stop. And then it turns it back on and it goes, and then it stops and then it turns back on. We call that short cycling. If your air conditioner is oversized, it's going to short cycle. It's going to run for very short periods of time, and it's going to blast cold air in for very short periods of time. And when it does that, it causes stratification, it causes cold spots, it causes warm spots, it uses a lot of energy, it shortens the life of your equipment, okay? So I can't emphasize enough that oversizing equipment is a very, very bad idea. But that's what contractors have been doing for years and years and years. I would hazard to say I could walk up to almost any house and just pretty much assume that the equipment is oversized for that house, because load calcs just rarely get done, okay? The only way that would not be true is if something happened to the house, like they added a bunch of glass or they removed all the ceiling insulation or the house developed a huge leak or something crazy like that. But that's the opposite direction we want to go, right? We want the houses to be more efficient so the equipment can get smaller and smaller, all right? So hopefully I just can't emphasize enough that oversizing equipment to be safe is not a good idea. In fact, the industry standard for sizing equipment is called Manual S, okay? ACCA ACA Manual S, and it says that it is perfectly acceptable to size your equipment for up to 10% less than the load calc. It is perfectly acceptable to size your equipment for 10% less. 90% of your load calc is an acceptable sizing criteria. Okay, so just be aware of that. And then they have maximum oversizing limits as well, okay, depending on the type. All right, so let's talk about the refrigerant cycle. I'm very cautious not to put you to sleep, okay? So temperature is the density of BTUs. How many BTUs do you have in a confined space? And the more BTUs you have in that confined space, the warmer that space is, okay? Think of a kitchen match. You got a room and you got all these floating kitchen matches in your room. The more kitchen matches you have floating around in this room, the warmer the room is going to be, okay? So, and then the other thing that's important to realize is everything, even a block of ice, has BTUs in it. It's just less of them. The colder something is, the less BTUs there are. There are BTUs in everything, no matter how cold it is. The only exception to that is absolute zero, which is only theoretically, or can only be obtained in certain very, very strict laboratory conditions, but we don't have anywhere near that. So even on a really, really, really cold day, even a block of ice has some BTUs in it. Okay, so keep that in mind. When you're heating something, you're adding, okay? And when you add BTUs to a confined space, the temperature goes up, unless those BTUs are escaping somehow, okay? But if you're adding BTUs to something, temperature goes up. When you're removing BTUs, that's cooling, okay? We already talked about that. If you remove BTUs at the same rate at which they're coming in, the temperature will remain constant, right? We talked about that already. Now, I don't want to, this is called the second law of thermodynamics, and that's what really puts people to sleep when you start talking about the laws of thermodynamics. That's what put me to sleep in college. But the second law of thermodynamics is pretty straightforward. It basically says heat will move from a warmer object to a colder object. So think of BTUs, these kitchen matches, they're antisocial. They don't like each other. So the more of them you have in one object, and you give them the opportunity to go where there's less of them, they will just naturally do that, okay? And that makes perfect sense. You take a warm block of metal and a cold block of metal. The warm block of metal has more BTUs in it than the cold one. You put those next to each other, and the BTUs are going to go from the warmer one. They're just going to naturally migrate into the cold one. Okay. A lot of people say, oh, the cold one's cooling the big one. No, the big one's, the warm one is heating the cold one. The BTUs are going into the cold one. Okay. And then when does it stop? It stops when the two blocks become the same temperature. Now there's the same number of BTUs in both of those blocks. So that heat transfer stops because there's no, one's not warmer or colder than the other. So the BTUs, doesn't matter where they go, it's going to be the same. Okay. So they stop moving. That's a really, really crude definition of the second law of thermodynamics. Okay. Now, here's the interesting thing. If you have a volume of, let's say, air or a compressible gas of some sort, and it's a certain volume, and you have a number of BTUs in there, remember, temperature is based on how dense those BTUs are, how close together they are. You can increase the heat of a confined space by reducing the volume. So you compress that air and those BTUs get closer together and they get warmer because they're closer together, okay? So that's a very interesting concept. And that's, I don't know if anybody scuba dives or anything like that. You've ever heard about scuba tanks? When they fill a scuba tank with air, that tank gets really, really hot because they're taking all this air that has BTUs in it and they're compressing it into a smaller space. Another, I don't have one here, but the little air cans that you spray to get the dust out of your computer keyboard. As that volume expands, the BTUs are getting farther, they're getting less dense, and it cools off. Okay, that's the principle that we're talking about. So by compressing a gas, you can make it warmer, and the same is true by increasing the volume with the same number of BTUs, you can make it colder. So you can make a volume of gas warmer or colder by changing its volume. That's a very interesting principle, okay? Now, colder or warmer will either attract or expel BTUs. So let's say we've got a room that's 70 degrees. Oops, excuse me. Let's say we've got a room that's 70 degrees and you've got this volume of gas that's 70 degrees, but then you expand it and cool it. There's more BTUs in the 70-degree air, and it's going to go inside that container because you've expanded it. You've cooled it down to 40 degrees by expanding it. And now the BTUs are going to go into that container. So you've actually attracted the BTUs into that container. You've captured BTUs simply by expanding that gas. Okay. Now oh, I got this jar of BTUs. What am I going to do with this jar of BTUs? Well, you take it outside and you smash it. And you smash those BTUs, you smash that jar down, and that makes it hotter. Okay. And now it's 100 degrees inside that jar, and it wants to go out. Well, let's say you do it in the room. So just by expanding it, you're sucking in BTUs. It's like a sponge, okay? By expanding it, you're sucking in BTUs. By compressing it, you're expelling them. Now, let's say you expand that, okay? and you take it outside and you smash it and you put them outside. You've just moved BTUs from the inside of the house to the outside of the house. Okay, so that's very important, this concept of expanding and compressing a fluid, a gas. Okay, it works on air, but not as well. They have found there are certain types of gases where when you compress it, it turns into a liquid. And when you expand it, it turns into a gas. And that change of phase makes it work 10 times better than just expanding a gas. Okay. By changing that phase, it works really, really well. So they've perfected this concept of sucking up BTUs and squeezing them out, sucking them up, squeezing them out by a special kind of gas, which we call a refrigerant. Okay. All right. Now, let's say we have a house at 70 degrees and let's say it's 90 degrees outside. We can actually, I've already kind of alluded to this, we can actually go inside the house, expand this gas, make the gas 40 degrees, suck up all these BTUs from a 70-degree house, take it outside, squish it down to make it 100 degrees and expel it to the 90-degree air because it's hotter than the outside air. So by making it colder than the inside air, we absorb BTUs, and then by making it hotter than the outside air, we expel BTUs. Okay, so it's a sponge. It's like putting a sponge in a bucket and squeezing it out, and putting a sponge in a bucket and squeezing it out. You can take water out of that bucket. That's exactly what we're doing with BTUs. We're absorbing BTUs on the inside where it's cool. It's actually cooler. And then we take them outside and dump them out where it's outside. So we can mechanically move heat the opposite direction that it wants to go. It's going to come into the house. If we can move it out faster than it's coming in, we can keep the house at a constant temperature. Isn't that fascinating? That's what the refrigerant cycle is all about. Okay. So so again, we're expanding the air from the inside where it's cool. We're taking out and we're squeezing the BTUs out. It's like a sponge. Okay. Now, spoiler alert, we can go the opposite direction. Even if it's cold outside and warmer inside, like on a cold day, let's say it's 70 outside. No, let's say it's 30 outside and 70 inside. Okay, we can absorb BTUs from that 30-degree air and bring them inside the house and squeeze them out by making that gas hotter than 70 degrees. If we can make it colder than 30, we can absorb BTUs. And then if we can bring it inside, make it hotter than 70, we can expel BTUs. So we can actually take water, we can use a sponge and put water back into our bucket. Okay. So that's what a heat pump is. So all the stuff I've been explaining before is air conditioning, removing BTUs from a house. Now we can do the exact same thing going the opposite direction. We can absorb heat from the outside and bring them to the inside. Okay. But we don't have containers that do this. Our air conditioner isn't a bunch of containers that's going in and out and in and out, in and out, in and out. Okay. It's actually a pipe. It's a continuous stream of refrigerant. And instead of having a container that expands, there's a spot in that cycle where the refrigerant expands and then it moves along the pipe and then it gets squeezed out. Okay, and that's sort of the evolution of the refrigerant cycle, is to contain everything inside of a closed loop. And in part of that loop, it expands, and in part of that loop, it's compressed. So think of it as a whole bunch of little teeny tiny containers that are being, microscopic containers that are going through this cycle. All right. So where it expands and absorbs heat, we call that the evaporator. And where it's squeezed, we call that the condenser. Okay. And in air conditioning, we can absorb cool heat. Okay. We can absorb heat from a cool space and pump it through the refrigerant cycle and expel it to the outside. Okay. The heat is going from the inside of the house where it's cooler to the outside of the house. And it's just like our containers, it's being expanded to be colder than the inside of the house and absorbing heat, gone outside and squeezed, the BTUs are being squeezed out. And it's just this continuous loop of refrigerant that does that, and that's an air conditioner. Okay. Let's see. I need 1 minute. Sorry, someone's knocking on my door twice. Let me go get that really quick. Talk amongst yourself for 1 second. I apologize. Oops.
I did want to take a minute to answer a question that we can answer while Russ is taking his quick break is are heat pumps all electric powered? And there's actually there are gas heat pumps, but they're not common. And we are only talking about electric powered heat pumps in our webinar today, and that is the kind of decarbonization strategy. So just hit a question there while you were gone.
Awesome. Sorry about that. That's the joy of living in the country and having your neighbors come over and pound on your door. You always wonder, it's like, oh my God, is there a fire outside or something like that? But it was not that big of a deal. All right, sorry about that. The joys of working from home. Okay, so hopefully we kind of established that the refrigerator cycle is a pretty amazing thing, right? It's you know, it's one of those things where like the first person who discovered that was like, oh my gosh, this is amazing. What are the things I can do with that? And you know, the refrigerant cycle for cooling has been around since the 30s. It's old and proven technology. Some of the interesting developments that have happened recently are new types of refrigerant, the actual the gas themselves. You know, everyone, you know, the old term for refrigerant is Freon. That's the old refrigerant that used to, and now they don't allow it anymore because it turns out if it escapes into the atmosphere, it's not good for the environment. And so they've come up with some new ones that are more environmentally friendly and more efficient. Okay. The other thing is the motors that drive this. So there's a big motor here in the compressor. Those motors have gotten a lot more efficient. The units themselves have gotten a lot more efficient. You may have noticed that air conditioners have gotten bigger over time. You know, a 2-ton air conditioner used to be, you know, you can put your arms around it. Now a 2-ton air conditioner is quite big, and a 5-ton air conditioner is gigantic. That just means they're more efficient. They have more surface area. They've learned how to improve this technology and make them really efficient. And heat pumps in particular, one of the big improvements has been controls, how they control. So anyway, so this next slide is basically the same thing. It's just it's going the opposite direction. So this first slide here, you're extracting BTUs from a cool house at 70 degrees and you're dumping it outside to hot air, which is 90 or 100 degrees outside. Okay, so that's an air conditioner. Now, a heat pump, is just the opposite. It takes BTUs from the cold outside air, say 30 degrees, and puts it into the warm house at least the same rate that the BTUs are escaping. Remember, our whole thing is to keep a constant temperature inside the house. Okay. It does a very good job of that. And the cool thing is, it's the exact same equipment that your air conditioner uses. The only difference is there's a little valve inside there that switches the direction of the refrigerant, okay, and some fancy controls. But other than that, a heat pump and an air conditioner are essentially the same exact piece of equipment, okay? So why not take advantage of that? All right, so we'll talk more about that. Now, why are heat pumps so darn efficient? Okay, so in terms of gas heat, a BTU from gas versus a BTU from electricity. Gas on a BTU per BTU basis, gas is cheaper than electricity. 1 BTU from gas is cheaper than 1 BTU from electricity. Okay, it used to be a simple equation of 3 times. Okay, now it depends on when you use the electricity and all this other stuff. But suffice it to say that 1 BTU of gas produced from gas is cheaper than 1 BTU produced from electricity. And until recently, well, you know, what most people think is when you think of electric heating, you think of electric resistance heating. So electric resistance heating is when you take electricity and you run it through a wire, and that wire gets hot, and so you produce heat from that electricity. Electric resistance heating is really efficient. It's like 99, almost 100%. Let's just call it 100% efficient. So every BTU worth of electricity you put into it, you get a BTU out of it. That is super efficient. Gas isn't that good. Okay, the most efficient gas furnace is like 95, 96%. Okay, you're still low. In the old days, the typical furnace you would buy was 78%. So 78% of the gas you put into it, you only got that many BTUs. You put 100% of gas, 100 units of gas, you only got 78 units of BTUs out of it. Okay, but it was still more cost effective because on a BTU per BTU basis, gas was cheaper. When you compare electric resistance to gas heating will win. Okay, so what's so special about heat pumps? Well, electric resistance heating takes electricity and converts it to heat. Okay, it turns those electrons into heat. Heat pumps cheat. They cheat in a good way. They cheat in the sense that they take that electricity, they don't turn it into heat. They say, hey, there's already heat laying around here. Let's just gather up some of this heat and use it. All right. It takes much less electricity to move heat from one place to another than it does to create heat. Much less electricity. That's why heat pumps are so efficient. Okay, so in this diagram here, you've got 5 BTUs worth of electricity. They go into an electric heater and you get 5 BTUs out of it. That's super efficient. That's 100% efficient. But heat pumps, you put 2 units of electricity into a heat pump and it finds 5 BTUs of heat in the air. So it's only taking 2 BTUs worth of electricity to move 5 BTUs. So it's kind of like creating them, but it's finding that it's stealing them from somewhere else. Okay, we don't care where they come from, generally speaking. Now we are making the outside air a little bit colder, but not noticeably so. Okay, and so that's why they're so efficient. They're moving heat from one place to the other. They're using BTUs that already exist, and it takes a lot less electricity to move heat than it does to create heat. Okay, so hopefully that sinks in. Okay. Now, why should we switch from gas to electricity? Or yeah, to heat pumps. Gas to heat pumps in particular, not electric resistance, but gas to heat pumps in particular. Okay. So let's just talk about some of the advantages. So a lot of people are concerned about heat pump technology. Oh, it's kind of new. You know, there's all these new equipment and stuff like that. It's not. Air conditioners, the technology that heat pumps run off of is the same technology as air conditioners, and they've been around since the 30s. Okay. They are a proven technology. No one's worried about air conditioner technology. They're like, oh, I don't know, this air conditioning stuff, this is kind of new. I'm not sure if I want to put this on my house. Air conditioners? No, nobody cares. They've been around forever. It's a proven technology. Air conditioners move heat from colder to warmer via refrigerant cycle. Heat pumps move heat from colder to warmer via refrigerant cycle. It's the exact same technology. It's the exact same technology. Heat pumps are basically air conditioners that run backwards in the wintertime. They have a reversing valve and they just click over and they run backwards in the wintertime. And this is a great quote. Every heat pump comes with free air conditioners. So if you're gonna put air conditioning, or if you're gonna put a heat pump on your house, guess what? It comes with free air conditioning. Okay. So every heat pump comes with free air conditioning. All right. Okay. So the technology's fine. Don't worry about the technology. Okay. And then a lot of people say, well, how cold can it be before a heat pump stops working? How cold can that air get before it'll stop pulling heat out of it? Well, here's a great example. What's the coldest freezer you've ever had in your house or ever seen? You know, you have a big chest freezer out in your garage, you keep things frozen rock solid. Okay. However cold it is inside that freezer, it is still extracting heat from that. And your freezer is a heat pump through refrigerant cycle, is extracting heat from that very, 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 very cold freezer and dumping it to the outside. Okay. So if it can work there, it can certainly work on a 30-degree day or a 24-degree day, or, you know, however cold it gets at night. Okay. It can certainly work just fine. And your heat pump compressor and everything is a much bigger unit than what's in your freezer too. The one in your freezer is teeny tiny compared to the one on your house. Okay. So if it can pull heat out of a very cold freezer, it can pull heat out of cold night air. Okay. I guarantee you. All right. The other thing is that is that there's a lot of very cold regions in the world. And I have friends in Minnesota who have just recently put heat pumps in their house and are monitoring them. And guess what? They're not even reaching design capacity yet. They haven't even, the temperature outside has gotten colder than the design temperature, and the heat pumps are still working fine. Okay. So they work in Minnesota. If they work in Minnesota, they will work in the Bay Area. Okay. In fact, they're ideal for the Bay Area climate, because one of the weird things about heat pumps is it's an air conditioner and a heater in one unit, and you can't like buy one with extra high heating and extra high cooling or something like that. The relationship between that heating and cooling capacity is always kind of fixed. Okay. And so certain climates where the heating load and the cooling load kind of fall into those ranges are the best places for heat pumps. If in really, really cold climates, you might have to actually oversize the air conditioner. Okay. But the Bay Area climate is perfect. What we have in most of Northern California, every place except like Truckee and Tahoe, is ideal for heat pumps. Now, you can put electric resistance heating in a heat pump. And in some climates, they call that supplementary heating. And so if for some reason if it gets really cold really fast and the heat pump can't keep up, this electric resistance supplementary heating will kick in and kind of boost the heat pump along. We don't need those in our climate. We do not need that in our climate. Heat pumps will keep up if designed properly. That's an important key I'm going to talk about in a minute. Now, you can have what we call electric resistance backup heating, which is only for emergency purposes. Only if your compressor were to fail do you want this heat to kick in. Okay. But I would avoid that if possible. Okay. If the electricity goes out, your gas furnace doesn't work. Okay. It runs off electricity too. So saying, oh, I don't want a heat pump because the electricity might go out, the only thing that's going to beat that is a wood stove. Okay. So if you're worried about the electricity going out and not having heat, you should have a wood stove or some other sort of like plug-in. Plug-in wouldn't work either. I do not bring propane in your house, for goodness sakes, but a wood stove is probably your best bet. Okay. But anyways, different issue. Okay. So advantages of heat pump space heating. The big one to me, honestly, my personal one is it's safer. Okay. There's no gas or explosion danger. You've seen, you remember the big explosion in the San Francisco area. There was a huge explosion in the Sacramento area not too long ago. So gas is it's an explosive product, and piping an explosive gas into your house just has never made sense to me. Okay. And then the burning of a natural gas gives off poisonous gases, carbon monoxide. Okay. And then, having an open flame in your garage or in your attic is a fire hazard. If you have, where do you store your gas tank for your lawnmower, in your garage, and not too far away is an open flame from your furnace and stuff like that. So all these reasons. And if you ever noticed, if you ever get a permit for anything, even replacing the faucet in your house, they will require that you put carbon monoxide detectors in your home. And they've been doing that for quite a while. And the reason is that the potential for something to go wrong with a gas furnace is much higher than people think, especially as these furnaces get older and older. The old furnaces had cast iron heat exchangers where all the flame is, and then the air blows across the outside of that. Well, those cracked after a while. The newer ones were pressed metal, and the expansion contraction, those got holes in them too. So the potential for something to go very, very wrong with a gas furnace is much higher than people realize, which is why carbon monoxide detectors are required for anything you do to your house. Okay, so that's an important key. Also, I know Chris is certified. I'm certified through BPI for combustion safety testing and stuff like that. And one of the first things that came to my mind as I was taking these combustion safety tests was, oh my gosh, how have we survived this long? It was kind of my first thing. So anyways, I realize I'm running out of time. So the other thing, advantages, simpler and cheaper, no gas pipes, no flue vents, no combustion air considerations. It's a lot easier to put in electric heat pumps than it is to put in gas heat. Lower maintenance, that's a big deal. Open up your furnace and look inside. If you have a gas furnace, open up. 90% of the things you see in there are safety things. Those all have to be, calibrated. They all go bad, and stuff like that. Another advantage of heat pumps is smaller size. Okay, you can, if you have a really small ADU, let's say, or a really small, dwelling unit, heat pumps come in much smaller sizes that are more appropriately sized to those small dwelling units. Cleaner, okay, we've all talked about that. Super efficient, talked about that. Okay, cost effective in many markets, depending on the cost of electricity and the cost of gas. Heat pump is cost effective compared to gas. Okay, in many markets, not all, but many. All right, disadvantages. The equipment itself, the controls and things like that are more complicated. It does take a little bit higher level technician to service some of these things, but that's getting better every day. Okay, the controls are more complicated. If you don't correctly set the controls, they may actually blow cold air during a certain time of the day, which is not good, but that can be overcome. Okay, these are all preventable disadvantages. They can be impacted by bad design. A gas furnace is a dumb beast. You put it on a house, it blows heat into the house. Heat pumps are like air conditioners, that the actual heating capacity depends on the design conditions. So on a really cold day, they don't work quite as much. Duct sizing is very important. If you don't properly size your ducts for a heat pump, it can impact that. But that's avoidable too. Hire a good contractor, hire a contractor that knows what they're doing, that does a good design. Your heat pump system will work just fine. Grid reliability issues. If everybody switched over to electricity, we might have brownouts and blackouts and things like that we're concerned about. Those things are being addressed. Okay, those things are being addressed. There's going to be some growing pains with that stuff, but for the most part, we're making improvements on that. Okay, heat pumps can run off of solar panels. They can run on battery backup. Okay, so that's all good stuff. One of the things is if you switch from gas to heat pumps, a disadvantage is that you may have to upgrade your electrical panel. You may not have enough capacity in your electrical panel, but there are rebates specifically to cover those costs. Okay, so that's a very good thing. All right. Let's talk about some different types of heat pumps for space heating. All right. Pretty straightforward. You got your good old-fashioned standard heat pump that's been around for years and years and years. Okay, we call this a typical split system or a ducted system. The fan coil unit is what would normally replace a furnace. Okay, no gas lines, no flue vents. That's all well and good. These have been around forever. In fact, the first house my wife and I bought back in 1988 had a heat pump heating in it. Worked great. Okay. Now, the new ones are what we call mini splits. A lot of the Japanese brands and things like that, they've been around for years and years. They're only in the last 10 or 12 years have started becoming very popular in the United States, and there's some different kinds. We've got ducted mini splits. So you've got an air handler, a little small air handler that fits in a drop ceiling, and it's all ducted. It's got a return supply ducts. Okay. And then you've got your condenser, you got your air handler that can be ducted or unducted. So the unducted ones look like this. They're wall cassettes or the ceiling cassettes. Now those are great for heating and cooling the room that they're in. The question is, can that heating and cooling get to the adjacent rooms, or is it better to duct them? Okay. The other really interesting thing is you can have one outdoor condenser serve multiple indoor units, and they can be ducted or unducted. Okay, and so this one outdoor unit can be connected to multiple units. That's a really cool thing. Okay, so it can serve multiple, we call those heads. Okay, multiple heads, which is really pretty cool actually. Okay, then most heat pumps that we talk about are what we call air source heat pumps. They're getting the BTUs from the air. BTUs don't have to come from air. There's other places to get BTUs. In fact, there's better places to get BTUs than air. There's places where the BTUs are more dense. Okay, but these are less common systems, and you have to have kind of special situations. You have there's water source. Okay, if you have a big pond or a lake or a stream where you can put a heat exchanger out in there, you can gather BTUs from the water. Those are water source. or geothermal, where they'll bury the pipes down in the ground and absorb heat from the ground itself. Okay. All right, that's it. Sorry, Chris. As usual.
Hey, no problem. There are a couple of questions I wanted to check in with you on.
Yep.
Let's see. The first was, will a heat pump take the place of my aging AC compressor and play nice with my Lennox heating and ventilation unit?
Okay, so if your Lennox that you're talking about is your furnace, there is something called dual fuel, and Chris, you'll have to address any rebate concerns or things like that. So your heat pump has the outdoor condenser, and then the indoor fan coil unit. That fan coil unit can be a furnace, okay, and we call that a dual fuel system. It takes a little special, systems. You want to match those correctly for them to work correctly. But yes, you can have your heat pump condenser that provides heating and cooling work with a gas furnace, but then the controls have to know when it's better to run on heat pump and when it's better to run on gas furnace. I've heard of some people disabling the gas side of it and just using their furnace as the air handler and just disconnecting the gas. I've heard, so that is possible too. But if you're going to do dual fuel, then you lose the benefits of the safety and the environmental issues and stuff like that. But it is possible. It is possible. It's called a dual fuel system.
So there were two questions about whether there were gas-powered heat pumps available, and just thought maybe you could comment.
Yeah, there is. there is a gas-powered condenser. And the first time I encountered this technology was in Willits, not too far from you guys. My friend had a cabin up in the mountains, and he went into this cabin. This was a long time ago, before I went to college, and he goes, "I have to light my refrigerator." I go, "What?" He goes, "Yeah, there's a pilot light on my refrigerator. I have to light my refrigerator." It was a propane powered refrigerator, and so there is that same technology of burning a gas to cause a heat phase change, which will cool the condenser and stuff like that. But they're very, very rare. They're very expensive, but it is there. But I think what people are probably thinking of when they think of gas-powered heat pumps is the dual fuel, where it's actually a gas furnace. It's just a regular air source heat pump, but it's the gas furnace is alternating between the heat pump heating and gas heating. But they do make a gas-powered condenser, which is I have yet to actually see one in action, but they're out there, yeah.
Yeah, and that was my take. They're not common at all. They are out there, but and the rebates are specifically for electric, pretty much air to air heat pumps or air to water heat pumps. So and let's see. So I think you've already addressed what happens to your heat if the power is out, because your newer furnaces won't operate during a power outage either. So I don't think we need to really dwell on that. The heat pump unit has to be outside the house, or could it be in the garage?
The condenser is just like an air conditioner. It has to be outside. Yeah. Now heat pump water heaters can go in your garage. That's actually a good place for heat pump water heaters, because then they can capture BTUs from the air inside the garage. But your condenser, because it needs so much air circulation, it has to be outside. Yeah.
It says my gas furnace and AC have worked okay for 30 years, probably inefficient. Heat pump is its expected life is 10 to 15 years now. Are they not as good as they used to be for reliability?
They're more just like cars, an old, I love old Volkswagens, and an old Volkswagen will run forever and the new Volkswagens won't. It's just they're a lot more precisely manufactured to be more efficient, and so I think that affects they're less rugged. So yeah, it's not that they're not made as well, it's just that they're more precisely manufactured. They're just more complicated, I guess, is the best way to put it. So their lifespan isn't quite as long. But the older style heat pumps, the ones that have been around for a long time, those have gone 25, 30 years easy. So yeah.
So there's a couple more since we're kind of running late, but I thought we could address these. One is, how does the noise from the compressor of a heat pump compare? I'm not sure. I guess it says compare with a heat pump, but maybe they mean an air conditioner.
Yeah, it's the heat pump that we had on our house would go every now and then, it would go into what's called defrost cycle, and it would make some kind of funny hissing bubbling sounds, and it was like, what's going on with this thing? It's perfectly normal. When it's actually running, it's no different. It's no different than an air AC compressor. Yeah, it's exactly the same. But it does go into these weird defrost cycles where it has to stop for a little while, and then like if any ice is built up on the condenser, it has to melt that ice and things like that. So it will make some weird noises when it does that. But that's all outside. That's the outdoor condenser that's making that noise.
So I think we're good for questions. There are a couple of questions about the Inflation Reduction Act. And what I'm going to do is put a great website link in the chat from Rewiring America, and you just enter your location and it actually gives you some fantastic information about what's available now and then what's coming in the next year. And so I'm going to just plop that into the chat there for y'all. And yes, there are some very exciting things happening at the federal level. Our understanding is the tax credits are currently active. However, the rebates, they're going to be funneled down to the state level, and it'll take some time to work out that administration. There's a couple of questions about how to find contractors. One issue here is if you're interested in the Bay Area Regional Energy Network Incentive Program, you would need to use a participating contractor. The presentation slides that you'll get in a few days will have the links to the BayREN program, and it's pretty easy to find. It's just the BayREN residential rebates. So you can find contractors that way. They have a great contractor search tool. For our program, the Sonoma County Energy Independence Program, we maintain a very robust list of participating contractors that you can search by specialty. And I'm going to just put a short link in the chat, but also you'll get information about the Skype program and the contractor database in the slides. So there's some great resources for finding contractors. There's a question about cost ranges, and it's really all over the place. It really depends on what system configuration you choose, whether you're going to use a ducted or ductless system. So that's where the contractors are really a great resource, because we can give you a ballpark ideas of pricing, but it really depends on your loads, the size system you need, the type of system you want. Sometimes folks want a ductless system. Sometimes you want a combination system. It's really all over the place, and it varies by manufacturer. So contractors, a good contractor is the best resource for pricing. And we always recommend, consistent with the Contractor State License Board, that you solicit a minimum of 3 bids. And over and over again, repeatedly, that's just proven to be a good practice. And I mean, it's not about the lowest price. It's really a lot about, do you have a qualified contractor? Do you feel comfortable working with them? Do they show up on time? Are they responsive? Do they include everything in their bid? So we offer a good resource in our division. We offer consulting. We can take a look at bids with you. We don't recommend particular contractors or manufacturers, but we can help translate bids for you. And so that's kind of a good resource. But again, it's all about a good contractor can really lead you through this process. And if you want incentives, the BayREN program does require participating contractors. The Sonoma Clean Power program does not, but it's all depends on, how you want to proceed. Again, you'll get a bunch of information in these slides, and we are happy to talk to you about your individual questions, so you can reach out to our office. Thanks so much, Russ. Great information.
Yeah, my email address in there too. If anybody has any design related questions, I'm happy to answer those. If your contractor is recommending that you replace all your ducts and you're not sure if that's a good idea and stuff like that, I'm happy to answer those kind of questions too. So, and yeah. There you go.
I see somebody has a raised hand, but I didn't think you could raise your hand. If
It
you
looks
have
like
a
you.
question, rather, I don't think that we can answer questions the way it's set up. But if you want to put them in the chat, that's how we're addressing questions. And we have lots of thank yous, Russ, really appreciate it. But there are a couple of participants who are attempting to raise their hand, and unfortunately, I can't really work with that. We're limited to the chat. So if you want to enter your questions in the chat, go for it. We'll hold for a minute or two. And this is a great opportunity to ask one of the most knowledgeable heat pump masters
Mhm.
in the area. So,
Mhm.
but I think we're good. If you do have additional questions, please reach out to our office. And again, Russ's contact information will be in the slides. And thanks for joining us today. Thanks, Russ.
You're welcome. My pleasure.
So what am I doing? I'm going to end.